at the very root of things, at the most fundamental level, there is a beautiful description to be found, a very simple idea which underlies all the laws of nature.
How can you be so sure?
I'm not sure. I'm not sure. But it may be true. And it may be that the beauty we find in a theory like Einstein's theory
Mhm.
is a reflection of that. 'Twas but a dream of thee, is a dream of the beauty at a much deeper level of the really fundamental theory. Now, of course, when Donne was talking about "'twas but a dream of thee," he
Mhm.
was talking about a mistress, or perhaps it had some religious significance, and with Donne the two are difficult to disentangle. But I'm talking, the dream is the dream of the final theory, a theory which is itself beautiful and whose beauty we see reflected imperfectly in the theories we now have.
The usefulness of our sense of beauty is a sign of our progress towards a
Yes,
final theory.
yes, I think it may be. Now, you ask, though, a very good question. How do we know that there is a beautiful, simple description of nature underlying everything? And we don't know, but there is a reason for suspecting it. And the reason is just the increasing simplicity of the ideas which describe nature. Uh, the description of nature that we have now is infinitely simpler than it was in the 19th century when there were separate sciences like physics and chemistry and biology, which were not thought to have any real relation
Mhm.
between. I mean, there were laws of chemistry and there were laws of physics. Laws of physics were divided into laws of optics and mechanics and electricity and magnetism. There had been a mild unification in the work of Maxwell that unified optics and electricity and magnetism. But now, so many of these things are brought into a common framework.
Mhm.
Nature has gotten, if more esoteric, more mathematical, more impersonal, still much simpler in the way we look at it and describe it. Now, I can imagine this growth in simplicity going on for many years to come. But I can't imagine it on forever. How can things get more and more simple?
Mhm.
They could get more and more complicated, but more and more simple. You would think eventually it has to come to an end. It has to converge to something which is the final simple theory. But I don't know that that's true. The concepts are increasingly foreign and impossible to explain except in mathematical terms. The the most adventurous theoretical physicists today have almost succeeded in giving up the idea of space and time, except as phenomena that arise at a certain level of approximation, but which do not appear in the underlying equations. For an ordinary physicist who lives in the world of particles colliding and electric currents and rays of light, it's very difficult to imagine formulating the equations that govern nature without having space and
Mhm.
time in at the very beginning. And yet that's the way the, the leading theorists of today are going. This is hard for me to understand. And the mathematics that goes into it is mathematics that physicists of my generation certainly didn't learn. Although we are comfortable with the equations of Einstein and Newton, we did learn that mathematics when we were in school. Uh, I've been pretty cautious about imagining what the final theory is. I think there was a time.
You're sure about its beauty, but for the
Well, I'm
rest,
sure about its beauty because if it isn't beautiful, we won't recognize it as the final theory. We will say, well, why is this what it is? And we will look for something more beautiful. So it may be the final in the sense that it's the best we can come up with, but it won't be what our heart's desire is. Um, it's just like you could say, I'm sure, I don't know who I will marry, but I'm sure that she will be beautiful because I won't marry her otherwise. And in my case, it did work out that way. I would say that principles of symmetry are one form of simplicity and inevitability. A symmetry principle is a statement that something looks the same from different points of view. Um, if you look at my face, you see little difference between the left and right. It's not perfect symmetry, but the human face is pretty good bilateral symmetry. The other things have a much higher degree of symmetry. Um, a cube, I don't have one handy to show you, but a cube,
No, this is not a cube.
well, we don't have any cubes here, but a cube would look the
We can
same
imagine.
from a number of different directions. You can look at the cube from top, from the side, it looks the same. A sphere has even more symmetry. These are just the symmetries of things, and they are of only minor significance. I mean, certainly it's not the most interesting thing about a human face is that it's symmetrical between left and right. Um, the symmetries that are interesting to the physicists are the symmetries of laws, the symmetries that say the laws of nature don't change when you change your point of view.
Mm-hmm.
For example, if I move my laboratory from Texas to Amsterdam, which I'm not proposing to do, I will discover the same laws of nature. Uh, the world will look different. The days will be shorter in winter. There'll be more rain. But so I will notice that there's a difference. But the laws, the physical laws, will be the same, whether
Mm-hmm.
discovered in Amsterdam or in Austin. Uh, and the symmetries of nature are the variety of different changes of point of view, which have that property that they don't change the laws of nature. And they involve translation, as I said, the movement of the laboratory from one position to another, rotation, the change in the orientation of the laboratory, and several others, some of them having nothing to do with space and time,
Mm-hmm.
some of them having to do with how we identify the elementary particles. There are symmetries that say the laws of nature don't change if everywhere I see this particle, I replace it with another particle, and vice versa. Or more complicated transformations can be done. Very often, when we don't understand the forces, uh, that we can still detect the fact that there is a certain degree of symmetry present.
Mm-hmm.
And in fact, when I was first a graduate student, much of the work of elementary particle physics had to do with working out the symmetries because we had no idea of the nature of the forces that were acting on the particles. And all we could do with any degree of confidence was to discover and test the symmetries of the particles. Now we're in much better position. In fact, now we're in a position where we recognize that the nature of the force itself follows from the symmetries. The forces are dictated by the symmetries. They could not be other than what they are. Uh, and my favorite example of this is gravitation as viewed from Einstein's point of view. It
Mm-hmm.
requires me to do a little demonstration standing up, but
Yeah.
if you don't mind, I will.
Yeah.
If I stand here, my arms hang loose at my side. Now, if I twirl around, I'm not going to do it very fast, but if I did this very fast, my arms, are drawn up. And then, if like an ice skater, I bring them down, I spin even faster.
Mm-hmm.
Uh, my arms are drawn up when I spin by what we sometimes casually call centrifugal force. And from the point of view of Newtonian mechanics, the reason that this effect exists is because you should really write the laws in a frame of reference which is not rotating. And it's only in that frame of reference that Newton's laws in their simplest form hold. And what you see when you rotate is the effect of the change of the frame of reference.
Mm-hmm.
Now, from Einstein's point of view, the answer is quite different. Einstein's point of view about space and time says that all frames of reference are equally good. It's a principle of symmetry. There are different ways of measuring, including working in a rotating laboratory,
Yeah.
so that you measure positions and times differently than if you were not rotating, and they're all equally good. So how does Einstein explain the fact that my arms are drawn up? Why does that happen when I spin and not when I just stand still? Well, Einstein points out, actually following Ernst Mach in this, that when you spin, there's something else that changes. If you look at the stars, you'll see, from a spinning point of view, they're rotating around the zenith.
Mm-hmm.
If you sat in a laboratory at night and you looked up at the sky and the laboratory was rotating, you would see the sky rotating around you. Uh, Mach asked, without being able to answer the question, is there some effect of the rotating universe which creates the effect of centrifugal force? And Einstein answered the question and said, yes, indeed, it is the force of gravitation. Now, ordinary gravity, as described by Newton, can't do that, because ordinary gravity, the kind of gravity we're familiar with in everyday life, is just simply an attraction,
Yeah.
and it can't do that. But in Einstein's general theory of relativity, a rotating body not only attracts things, but also sets up a field of force which is a little like a magnetic field. And the rotation of the whole heavens around us produces, through Einstein's form of gravitational equations, the centrifugal force that pulls our arms up. So, in other words, now, if gravity didn't exist, there could be no symmetry between the rotating frame of reference and the
Mm-hmm.
frame of reference at rest.
Mm-hmm.
So, therefore, the the statement that there must be a symmetry, the demand for symmetry between these two frames of reference, requires the existence of gravity. The existence of gravitation can be deduced from that symmetry principle. Because what else could be producing the centrifugal force? Some force. And that force, when you work out its details, is just the gravitational force as described by Einstein's equations. And today, the other forces of nature, electric, magnetic, weak nuclear forces, which are responsible for beta decay, for radioactive decay, and for processes in the sun that produce the heat of the sun, and the strong nuclear force which holds the quarks together inside the nucleus of the atom. All of the all of these forces, all the forces we know in nature, arise from principles of symmetry and can be explained in terms of principles of symmetry. So principles of symmetry are the deepest things we know about nature. And it may be that a truly fundamental theory will be simply encapsulated in one simple statement of a symmetry principle. We don't know what that is. It may have nothing to do with ordinary space or time, may have nothing to do with the particles we see in our laboratories today. It may be very hard for us to guess. Maybe we're not smart enough to figure out what it is. But I would not be at all surprised if, at their deepest level, the laws of nature took the form of symmetry.